Hello everyone, I'm Wei. Today I will be presenting our recent work, MoveScore, and our metrics for test generation evaluation. What is test generations? For examples, machine translation is one of the most popular test generation tasks. Um, the goal is to train a machine translation system which can, for example, translate English sentences into German. Another example is test summarizations, which aims to summarizing multiple documents into a short summaries. Now we want to know how good systems translations and system summaries are. In the current evaluation setup, human written reference are always provided in a way that we can compare them with the system generated test by using a matrix. For example, we can use a matrix to measure to what degree system translations can accurately convey the meanings of the human reference. And also, we want to know how fluent these system translations are. For example, whether these system translations have ungrammatical errors. In this case, we don't need to access to human reference, and instead we just use the language models to score the system translations. Because language models is modeling the joint probability of co-occurrent words in text. So ungrammatical words are supposed to be appeared very few times in text. Then the language model will offer ungrammatical sentences very low score. Now let's see what metrics are being used. The most popular one is Blue Score, which is the metric to evaluate translation quality of system translations. In general, Blue Score accounts how many words are overlapped between system translations and human reference. We have many different ways to compute word overlaps. For example, we can count repeated unigrams divided by the number of words in system translations in order to get a unigram position P1. Similarly, we can get bigram position and trigram positions. Then we can make the geometric mean of them in order to get the final Blue Score. But be careful, sometimes the Blue Score could be inflated if system translations are too short. For example, if we have the reference as I am a boy and the system translation I am, and the second system translation he is a boy. Then if we calculate the unigram position of them, then for the first system translations, we can see there are the two words overlapping in system translation and the human reference. So the P1 would be 2 divided by 2 because they only have two words in the system translations, right? So we will get the full score. And if we look at the second translation, and the P1 would be 2 divided by 4, become 0.5. So Blue Score think the system translation 1 has the better quality than the later one. But obviously, it is not, right? So that's the reasons why we need add a parity term to penalize the short system translations. The next metric is HUGE, which is to evaluate the quality of system summaries, different from machine translation. System summary has very large diversity in meanings because it's generated from multiple documents. So in the evaluation setup, multiple human references are always involved to evaluate the quality of every system summaries. So in this case, we compute the word overlaps between system summaries with individual human reference. Then we do the average in order to get the final group score. Other metrics like meteor and CIDRs and etc. are also very popular for test generation evaluations. If you are interested, please refer to the literature for further details. Okay, let's see the challenges for these metrics. Firstly, these metrics are all compute word overlaps of system-generated text and reference, so they cannot account for the changes in semantics. For examples, we have a system translations. Here, Obama speaks to the media in Illinois, and the reference text, the president greets the press in Chicago. Those two tests, they don't have any word overlaps, right? But obviously, they speak to the same things. Let's see the challenges in these metrics. Firstly, these metrics all compute the word overlaps between system-generated text and the reference, correct? But they cannot account for the changes in semantics. For examples here, system test Obama speaks to the media in Illinois, and reference test says the president greets the press in Chicago. Both two tests, we don't see any word overlaps in both two tests, but obviously they are speaking the same things. The second challenge of these metrics is they are very against human judgments. For example, suppose we have a matrix M which assigned the score to system translations by comparing it with human reference. And we also collect the human score which reflects the quality of these system translations. So then suppose we have many of such pairs, then we can compute the correlations between the matrix M and the human scores, right? And this is exactly the setups where our results here come from. Mover score is our work, and we see the previous metrics are clearly have very poor correlations with the human judgments, right? And we speculate that the reason is because these metrics only count word overlaps, but they don't consider the semantic changes in system translations and human references. As you see, this is a very active topic. Many novel metrics have shown that since last year. So I will be very happy if you are interested in doing a thesis in these topics. Please feel free to reach out to me. Let's see the progress of evaluation metrics in the last decade. Metrics could be labeled into three groups: lexical metrics, semantic, and supervised metrics in terms of their different implementations. Lexical metrics only accounts for word overlaps, but semantic metrics use word embeddings to account for the semantic changes, while supervised metrics use the supervision from human judgments to train a matrix. Firstly, we know that lexical and semantic metrics both are unsupervised, but we see the semantic metrics oftentimes outperform the lexical metrics. And before 2019, the supervised metrics dominate the dominate the performance in these areas, like Rusa. But in 2019, when the bird imbalance comes into place and the two novel metrics, bird score and our Moore score, both are unsupervised, but they both outperform unsupervised metrics. Rusa. Now I will introduce Moore score. First, we know that previous metrics are often task specific. For example, blue score is proposed for machine translation, while hood score is proposed for test summarization. But our proposal is to provide a versatile matrix which can be used on a number of test generation tasks. Moore score is a set-based similarity matrix to measure the semantic distance between two sequences of words via summing up the transportation cost. Now let's take a look at an examples here. We have system translations and human reference. Now we wanted to compute the semantic distance between them, but we ignored all the functional words in both tests. In the first steps, we get word embeddings for each word in system translations and human reference. Then we randomly choose a word Obama in system translations and to compute its distance to every word in human reference. Then we can find the nearest word president to then we can find the nearest word president by the minimum distance. Then we repeat these operations many times. Until many words. Then we repeat these iterations many times until find the until we find the 1-to-1 word alignments between two tests, between system translation and human reference. Then we sum them up as the semantic distance between two tests, where lower score means the lower score means two tests are more similar. Instead of greedy one-to-one alignment, we turn to optimal many-to-many alignment, which we assume is more precisely to reflect the semantic distance between two tests. For example, we say Obama is 80% related to president and 20% related to grades. Then we do this repeatedly until we find our word alignments. Then we sum them up to get the final semantic distance score. In summary, suppose we have a system translation y and a human reference y star. First, we obtain the embedding of every word in y and y star. Then we compute a distance matrix C, which accounts for the distance of arbitrary word pairs. Then we find an optimal alignment matrix F by solving a linear programming problems. Then we sum them up to get the final semantic distance between system translation and human reference. Okay, let's have a look at the results in machine translations. First, we note that a semantic matrix called MINT 2.0 outperforms lexical metrics like sentence bird and character plus plus. But they still perform worse than supervised metrics like Blend and Rusa. And you can see that the recent semantic metrics like bird score and the Moore score, which both couple with but word embeddings, they perform even much better than supervised matches. Now let's see some analysis on how these metrics judge system translations with different levels of translation quality. First, we label system translation into two groups, bad quality and good quality. Then we ask the sentence blue metrics and our metrics more score to judge the system translations. On the left side, we see the sentence blues often assign low score to bad translations, but some good system translations are also assigned low scores, which means sentence blue is difficult to distinguish bad system translation from good ones. However, on the right side, we see our newer score can correctly assign low score to bad system translations and high score to good system translations. Let's see the results in test summarization. The trend is very similar to machine translations, where we can see bird score and mover score are able to outperform everything, but there's a one point which is different from machine translation is that semantic matrix here is very bad. Semantic it's perform much worse than the lexical matrix. I don't have a very good reasons for that, but I assume maybe the maybe the data sets in test summarization give some reasons, or the basic embedding used in root 1 and root 2 are not so successful because we see the bird score and the moon score, which both coupled with more powerful bird word embeddings can outperform even supervised metrics. Now let's see the results in image captioning. The goal of this task is to generate a caption from a given image. And we see the bird score and the mover score can outperform previous metrics by a large margin, except for the LEIC, which is a supervised matrix trained by the supervision from not only from system-generated caption, reference, and human score, but also it uses the information of the images, while other metrics judge the quality of captions only by a reliance of the human captions. So we think this makes a big difference. For question answering, we see the Moore score also outperforms previous metrics. In conclusion, Moore score is a new matrix combining word embeddings and Earth-mover distance. It achieves high correlations with human judgments on a number of text generation tasks. It's also able to distinguish low quality from high quality system generated tests. Please feel free to reach out if you have other questions or you are interested in doing a series in this topic. Thank you.